Thermodynamics, page number 62, question number 3. AC Verma. A 100 kg block is started with a speed of 2 meter per second on a long rough belt kept fixed on a horizontal position. The coefficient of kinetic friction between the block and the belt is 0.2. Calculate the change in internal energy of the block belt system as the block comes to a stop on the belt. So, question number 3. AC Verma, Thermodynamics, page number 62. The mass of the block is 100 kg and the speed of the block is 2 meter per second and the coefficient of friction is 0.2. So calculate the change in the internal energy of the block belt system as the block comes to a stop on the belt. So initially what happens when I'm putting the block on the belt, this is the belt, and when I'm putting the mass over here, it starts slipping. When I'm putting this, initially it will start slipping, right? And why will it start slipping? Due to the friction. Okay, and when it comes to rest, that means what happens? The body loses its kinetic energy. Initially it was moving with a velocity v. Now after some time it comes to rest with respect to the belt. So it loses its kinetic energy when it comes to rest. So what happens? It loses its kinetic energy, and that is responsible for the change in the internal energy of the block belt system. And this is equal to what? Half mv square. This is the loss of kinetic energy, and this is giving the change in internal energy. So half m is 100, v is 2 square, so it is 200 joule. Initially the block has velocity, so it has kinetic energy with respect to the belt, but when it comes to rest, there is no kinetic energy of the block with respect to the belt. So this is the change in internal energy of the block belt system. If somebody has kinetic energy and if it loses that, so the system gains an internal energy, kinetic energy converted into internal energy. This is the explanation for A. B part, consider the situation from a frame of reference moving at 2 meter per second along the initial velocity of the block. As seen from this frame, the block is gently put on a moving belt, and in due time the block starts moving with the belt at 2 meter per second. Calculate the increase in the kinetic energy of the block as it stops slipping past the belt. So now from another reference frame, I am watching this. I'm in another reference frame which has the same speed of the block. So initially I am seeing that there is no velocity of this with respect to this, because it is also moving with 2 meter per second and the block is also moving with the speed 2 meter per second. So initially it has no kinetic energy with respect to this frame, but after stopping this frame is moving with velocity 2 meter per second, but it comes to rest with respect to the belt. With respect to the belt, it comes to rest. So it will traveling along this direction, and this will appear as it is going away because it is moving. This belt is at rest, this belt is at rest, so it will start moving along this direction. So from this frame it gets a kinetic energy equal to half mv square. This is also 200 joule. In C part, find the work done in this frame by the external. Find the work done in this frame by the external force holding the belt. Okay, because of the fact कि the system, the external force which is holding this block, so which system? Find the work done in this frame by the external force holding the belt. Mane, what you can say, the meaning is that the second belt is holded by some system. So what amount of holding this system, the initial system, somebody is holding this. So what amount of work should be done on the system? Look, due to the kinetic energy of this, the belt will try to move in the opposite direction. Okay, the belt will try to move in the opposite direction. So in this case, it have to supply to balance the kinetic energy of this, and even it will try to slip in the opposite direction. That's why another half mv square plus mu mg into s, if the block slips by a distance s, this amount of work should be done by the external system. And even mu mg is equal to half mv square, so half mv square plus half mv square, meaning 400 joule of work should be done. Is it clear, the third point? It is moving with kinetic energy half mv square, and due to this it will try to slip away, and in that case half mv square must be equal to mu mgs. So the external system have to provide this amount of energy and even this amount of energy. So total energy is 400 joule. It should be supplied on this frame. This is the explanation of part C.